This is Principal Component Analysis explained from scratch with a focus on AI for healthcare. The link to the notebook is in the description. Principal Component Analysis, or PCA, is a technique to reduce the number of dimensions or features in a dataset while retaining as much information as possible. But what does this mean and how do we implement it in Python? First, we need to ask, what does it even mean to reduce dimensions or to reduce the number of features in our dataset? Consider we have a dataset of 5 subjects where we know their age and shoe size. In this case, the shoe sizes are pretty much the same while their ages vary a lot more. As we can see here, the shoe sizes only vary a little bit while the age is pretty spread out along this axis. And since the age axis has more variation, we say it captures more of the information or more of the spread in our subject population. In this case, we can completely remove the shoe size axis and still retain most of the variation in the dataset. Put another way, the age axis helps us distinguish between subjects easier than the shoe size axis. It helps us determine which of these patients or subjects are related to one of these ages. We can completely remove the shoe size axis and still have pretty high confidence. But now consider a scenario where we have about an equal spread among features. Let's say we have both age and we have variable income. Now, the axis of most variation, which is this line over here, is tilted. We can no longer keep just our original features and pick among them. We cannot just remove the age axis or remove the income axis in its entirety. Instead, we need to construct new features or new axes by combining our original features. And these new directions in the data, that is our PCA features. PCA computes the directions with most variation in our dataset, like here, which gives us new features that are sums of the previous ones. And PCA, or Principal Component Analysis, is a method for finding these directions mathematically. And the steps that we take is to find the new directions of most variation, and then we project. Then we just put all our data points onto those axes and these new features to reduce the number of dimensions while retaining as much information as possible. Just as we did here, we can project the shoe size onto the age side, on the age axis. We still lose some of information, but we keep most of the spread. So that's the theory part. Let's go into Python. The first thing we'll have to do is import packages in our dataset. So I'll use NumPy, Pandas, and also sklearn to load the breast cancer dataset. We load a dataset using dataset is equal to load breast cancer and get the X from the data and Y from the target. And running this cell is going to show us that we have 569 subjects and 30 different features. And each row has a label if the breast cancer is malignant or harmful or benign, not harmful. And we can look at the DF right here and see all our 30 features. Everything, there are numbers that describe different features in our data sets. The next step is to standardize the data, because with PCA, our goal is to construct new features that capture most of the information contained in these variables to reduce the number of dimensions. But first, we need to standardize the data and make sure it is centered and the features have the same scale. Otherwise, this might skew the variation. For example, age might only go from 0 to 100, while income can go anywhere from 100 and, who knows high. So to standardize it, we're going to remove or just subtract the mean. That's going to mean center it. And then we divide by the standard deviation to also kind of account for these differences in scale. After that, we compute the covariance matrix. And this matrix is essentially all the features compared to each other pairwise to see how they act together. The covariance matrix answers how features are correlated with each other. And this helps us find the direction of most variation. Just like we can see up above, that these two features kind of correlate with each other, they move together. And from that, we can deduce these axes of variation. And we use the np.cov to compute the covariance matrix. And we set row var to false. And this is from the documentation where we would say that each column is a feature and not each row. And just like that, it's going to take the 30 dimensions that we have and it's going to make a square 30 by 30 matrix. And the next step is to compute eigenvectors and eigenvalues. Because the special thing about the covariance matrix is that it is symmetric and it's square. And according to the spectral theorem in linear algebra, a symmetric matrix always has an orthogonal set of eigenvectors as a basis. And what does this mean? Well, it means that a symmetric matrix, just like our covariance matrix, can be described by a coordinate system with a set of max n dimensions, and we use the eigenvectors, and they are at right angles of each other. So the eigenvectors here represent the new directions in our data set. It's like a new axis. Instead of using the x and y axes, we're using the eigenvector axes, where the data is most spread out along those axes instead. Because then we can start removing these dimensions and have them aligned just like we could when we only had one axis made rough or spread. And the eigenvalues represent how much variance we have along each direction. So by sorting the eigenvectors, or new features, by the eigenvalues, so it's going to be the eigenvalues, which is the variance of our most important features, we can find our most important new components. And these are our principal components. So you compute the eigenvalues and the eigenvectors using np.linalg.eigenvector of the covariance matrix, which we computed above. And we can then sort the indexes by the eigenvalues and get the eigenvalues and eigenvectors sorted. And now the final step is to decide how many new dimensions to keep and project our standardized data onto our new coordinate system. And the projection formula in linear algebra is this thing where we have the vector we want to project, and then you take a whole bunch of dot products. But the thing is, we actually only need this part, the scalar part. We don't need to multiply it again by a vector, because this scalar right here is just saying this is like the feature, how much spread out are we along this vector. And also, because we have normalized eigenvectors, the denominator becomes 1 because their lengths are 1. So that's why we only need to compute this dot product right here between our standardized x vector and the eigenvector. And that's exactly what we do. So we just keep our top two eigenvectors, and then we take the dot product to compute the projected new feature. And this is everything we need, because now we can plot the results. So right here, I'm just taking scatter, and I'm plotting the 0 and the 1, so the two principal components that we just computed. And then I'm just adding a little legend, some titles, and showing it. And when we do, we can now see that we're just reducing this 30-dimension data set into a 2-dimensional data set. And already here, we can kind of see two groups of data. 1, which seems to be the malignant one, and 1 being the benign one. And that's it. We just coded PCA from scratch. And if we put it all together, we have the following. So we can define a class called myPCA, where we have self.endComponents, that's the components we want to keep. Then the computed components right here. We then standardize the X by removing the mean, dividing by the standard deviation, computing the covariance matrix, getting the eigenvalues and their eigenvectors, our new axes in our data space, and then we're getting the top ones and only keeping as many as we want. And then to transform our data set from this higher dimensional space to this lower dimensional space, we project it onto it by taking the dot product, and we return that. And then we can use it as before. We say PCA is my PCA with 2. We then fit it on our data, and then we transform it and plot it. And here we go, we get the same result again. Now, if we don't want to repeat the steps and always have to do all of those steps every time we want to use PCA, we can also use scikit-learn. So here we can import PCA and standard scalar to do this standardization. So again, I'll just compute a new PCA instance, but this time using the scikit-learn PCA. And then I'm going to scale my X, and then I'm going to project my X onto this. And if we do plot PCA, again, we can get a similar result. And with scikit-learn, we can also see how much variation are all of these components actually describing using the explained variance. And from here, we can see that the first principal component captures about 13.3% of the information, and the second one is like 5.7% of the explained variance. And what we can do, instead of specifying how many components to keep, we can also see the percentage of information that we want to keep. So right here, I'm saying I want 95% of information remaining. And when we do that, we can see that we have a new shape of 569,10, which means that we needed to retain 10 features to capture 95% amount of the information data. And again, these are not the 10 features from before, these are 10 newly constructed features using our eigenvectors. And finally, we can see how a predictive model would perform on our reduced dataset. So again, from scikit-learn, we import train test split. We then split our original dataset that's scaled, but using all the features. But then again, we're computing the PCA features and splitting that up with a test size of 0.2 and a random state. And then I'm going to import a linear model called logistic regression. And again, we're going to instantiate that and fit it on our X train and Y train and score it. So using all features, we get a 98% accuracy. But using our PCA features, so only using 2 features, we get about 93% performance. So yes, we can see a small drop in performance because we're removing a lot of that information, but we're still retaining enough to get this high performance. So we're still retaining most of the information that was found in all of these 30 features. And with that, congratulations on making it all the way through. If you found this notebook or tutorial helpful, please consider sharing it and making it easier for other people to find it. So that was PCA with AI for Healthcare. Thank you for watching.